Greetings and welcome to the introduction to astronomy. In this week's discussion on the celestial sphere, we are going to talk about ecliptic coordinates and see how they can be used to measure positions. So what are ecliptic coordinates? Well, they're another way of measuring positions. And we've talked about right ascension and declination previously. Those were measured relative to the celestial equator and the celestial poles. The ecliptic coordinates, on the other hand, are measured, as you might guess from the name, relative to the ecliptic. Now, the ecliptic is the solid line pictured here, which shows the path of the sun. And that is the path that the sun appears to take over the course of the year. And it is going to be tilted relative to the celestial equator by a specific amount, which is 23.5 degrees. And if you recall, that is the tilt of Earth's axis. So the celestial equator is the projection of Earth's equator. The ecliptic is always tilted relative to that. And we measure two coordinates, just as we had right ascension and declination. We have latitude, which is comparable to declination. And we have longitude, which is comparable to right ascension. Now the latitude is given by the Greek letter beta here and is measured from the ecliptic up to the position of the star. So that would give you your ecliptic latitude. Now you can see that would be different because if you measure declination, you go all the way down here, in this case to the celestial equator, to measure it. Now the longitude is measured from the vernal equinox. So the vernal equinox to this point would then give you the ecliptic longitude. And again, it's measured along the ecliptic, not along the celestial equator. So the coordinates are going to be different than you would get for the equatorial coordinates that we've used previously. Now the reference points here are the vernal equinox, just as we use for the coordinate right ascension. The vernal equinox is actually the same here and works for both, because it is the place where the ecliptic and the celestial equator intersect. You will also have the ecliptic itself comparable to the equator, and the ecliptic poles, which will be comparable to the north and south celestial poles on Earth. They will just be offset. Remember that they're not going to be exactly the same because of that tilt of Earth's axis. Now, were the Earth not tilted, then ecliptic coordinates would be exactly the same as the equatorial coordinates that we looked at previously. Now, why? What are the uses for ecliptic coordinates? Well, one primary use would be using solar system objects, because this is the path of the sun and our solar system is relatively flat. The other objects in our solar system are going to be always be very close to the ecliptic and will have small ecliptic latitudes, making this a very convenient coordinate system that we could use to measure the positions of, say, the planets or some of the larger asteroids or any other object that really stays close to the ecliptic. So that really applies to those type of objects, but could be used to use any object. It's just that the ecliptic latitudes are all going to be very small because those planets are really very close to the ecliptic. So let's go ahead and finish up here with our summary and talk about what we've looked at. And what we've said is, first of all, that ecliptic coordinates are measured relative to the ecliptic, not the celestial equator, as with the previous coordinate system we looked at. We can use the ecliptic latitude and longitude to define the position of an object on the sky. And we talked about how these are used for solar system objects, which generally lie in the plane of the ecliptic. So that concludes this celestial sphere discussion on ecliptic coordinates. We'll be back again next week for another topic on the celestial sphere. So until then, have a great day, everyone, and I will see you in class.